Okay, so in today's lecture, we are going to look at a few analog IC building blocks. We have already looked into many of these building blocks, or for example, we have looked into common source amplifier, common gate amplifier, common drain or source follower type of amplifiers as well. And we have looked into current mirrors a little bit. So in today's lecture, we're going to look at a few different analog IC building blocks in the form of current mirrors. So we'll be looking into a little bit more details into mirroring a particular amount of current. And we'll also look into differential amplifier, which will be one of the most important blocks to consider when you are designing an op-amp. Okay. So as I said in the beginning of this course, is that eventually we'll try to learn what is there inside your op-amp. And differential amplifiers will be one of the most important things that is there inside the op-amp as the first stage. And now that you have a good idea about, let's say, single stage common source amplifier, you'll see differential amplifiers will become very easy to understand. Okay, but before going there, current mirrors, we have discussed a little bit about this in the last lecture itself. So the idea is that if you have an external current coming in the form of this I1, that's the current source. So that's something you can connect externally. What you can do on the right hand side here is that you can mirror this current, the I1 current, into many different currents such as I2, I3, I4, and so on, something that we had discussed in the previous lecture. So if you just connect another NMOS device over there, and that current is I3, you'll have a ratio between I3 and I1, which will be determined by the ratio or the aspect ratio of the transistors that you are using over here. For example, I2, again, something that we have proved in the last lecture, I2 is the current flowing through this transistor, and that will be equal to K2 over K1 times I1. So the ratio of the device transconductances, and eventually it will become a ratio of the widths, because device transconductance, this factor K, as you know, is equal to mu times COX times W over L. So if you assume that the mobility of these two transistors are equal, which will almost be equal, because eventually mobility is a function of the charge carrier. In this case, they're the electrons. The COX or the oxide capacitance, they will also be same for the same technology node, for the same thickness of oxide, and so on. And again, if you assume that the lengths of the two transistors are equal, okay, in that case, K2 over K1 will just be W2 over W1, or the ratio of the widths of the two transistors. And if you keep on mirroring this current on the right hand side with more and more number of transistors, you can definitely do that. So from one single reference source, you can create multiple mirrored current using this approach. And how this will be useful, because you can use each of these mirrored currents as a biasing source for your circuits. And once we study differential amplifiers, this will become even more clearer that why we may need these many mirrored current sources. So these are just some of the functions of the current mirrors that we had discussed in the previous lecture. That if you are designing your current mirror in a way that you are sourcing a current, let's say you are designing you are mirroring a current source which looks like that, and then whatever goes here is basically your load. So this may go into an NMOS block, for example, right? So that you are sourcing the current if you are creating the current in this way. On the other hand, this is called a current sink, where you have connected a current source, but the current is going to the ground. So whichever device it is drawing the current from, for that device, this will work as a current sink. So there are two different terminologies when you are designing current mirrors, whether you are designing a source or you are designing a sink. So usually if you are designing a source, that current is sourced into a device. And as you know, for the NMOS, the current flows from the drain to the source of that particular device. So I'm talking about two different sources here. One is the current source, and here it is the source terminal of the device. You know that the current flows from the drain to source for the NMOS. So for this particular configuration, you'll be sourcing the current into the drain of the NMOS. On the other hand, if you're sinking current, most likely you're doing it from a PMOS. So let me draw it in a different way. So for the PMOS, the current flows from the source terminal to the drain terminal. So source to drain, and then it gets synced into the ground. So this could also be a very interesting topology. You will see more examples, so this will become much more clearer. But for now, let's just assume that there could be two different topologies possible. One of them would be called a source, the other one would be called a sink, whenever you're designing these current meters. So what is the potential application? So for example, you can use these current meters when you are trying to create, for example, digital to analog converters. So what is meant by digital to analog converters or DACs? So you may have heard about this terminology that digital to analog converters, they convert digital signal to analog signal. Right? So for example, real world signals are always analog. If you're thinking about audio signals, for example, or if you're thinking about let's say an analog video frame that gets captured in a camera initially, then you definitely have to digitize it, right? So a CMOS image sensor gives you analog signal, and then you have to convert it into digital whenever you're trying to like capture a photo with your digital camera. So that's the analog to digital conversion part. Similarly, you can create digital to analog. So let's say, for example, let's just take the example of this microphone. What this microphone is doing is that it's taking my audio signals from my voice whenever I'm speaking. It's taking in the audio signals, it's digitizing it, it's amplifying it, and then using a speaker, maybe even at the back end of this room, you are able to hear me very well because there is a speaker. Now the speaker does a digital to analog conversion if it is a digital speaker. Okay. So that's another example of a device where you may need a data conversion. So this is sometimes called data conversion, that you are converting digital data to analog or analog data to digital. So this is an example of digital to analog conversion. What it will mean is that you will have digital bits. So what are digital bits? Some of you have taken the digital electronics class, and you know that in digital, everything is represented with a 1 or a 0. So there is no 5 millivolt, there is no 100 millivolt, there's no concept of 1 volt. It's just a digital 1 and a digital 0, or a high, a logic high, and a logic low signal. Now, if you have multiple of those logic high and logic low signals, and some of you already know about all of this, so this could seem very trivial, is that let's say if you have a bit stream which represents 1, 1, and 0. So 0 is the LSB, so this is the LSB, and this is the MSB. What is the equivalent integer representation of this? 6, right? So this, because the third bit represents 4, the second bit represents 2, and the LSB represents a 1, right? If you are converting this to integer. So this will represent this number, integer number 6. So let's say if you have a 6 volt voltage and you are trying to convert it to equivalent digital representation. So 6 volt can be represented as 110 volts, right? In your if you are choosing to represent it that way. On the other hand, if you have 110, then you are actually representing 6 volts in the analog domain. So this is in digital domain, and this is in analog domain, for example. Right? So if you are talking about a particular voltage, it's in the analog domain. Now, how to sort of convert this digital data of 110 to 6 volts, for example, or let's say the corresponding current with respect to 6 volt. Let's say you have a 1 kilo ohm resistance, and you have this 6 volt voltage across that resistance. So the amount of current drawn through that resistance, or current passing through that resistance, will be 6 milliampere. So how do you convert this digital data of 110 into equivalent amount of voltage or current? So this is one application of this current mirrored architecture. So let's just say, for example, that you have a reference current, and then you are mirroring that reference current into this branch, that branch, this one, and that one. And of course, you may have many other branches in between. And all of these branches are controlled by these digital switches. Let's say D1, D2, D3, up to Dn. And let's say D1 is the LSB, and Dn is the MSB. So this represents a value which should be represented as a quantity which is just 1x, 1 times of the minimum quantity that you are trying to represent. This will represent a value which will be 2x. This will represent a value which is 4x, and so on for the minimum as compared to the minimum value. This is exactly same as how you represent the digital and analog. So your LSB size is half of that of the second LSB size, or in other words, this one when represented into equivalent analog forms, will be 2 times more important than the LSB. So that's why it's called the least significant bit. The LSB is least significant. The next bit will be second least significant, and so on. And the highest bit will be the most significant number. So you have to, if you have to assign weights in binary, you do a binary weighted representation, right? So this is 1x, 2x, 4x, and so on. So what we are doing here is exactly the same thing. You can have 1x current flowing through this branch. You can have 2x current flowing through this branch. You can have 4x current flowing through this branch, and so on. If you have the sizes of this transistor, so let's say this is W0, or let's just call it W0. That's the width of the reference transistor, and width of this first transistor is W1. Width of this one is W2. Width of this is W3, and so on. So what you can choose is the ratio of W1 over W0 to be 1x. The ratio of W2 over W0 to be 2x. The ratio of W3 over W0 to be 4x, and so on. Which means that the current that will be flowing through this branches will be 1x. Here you'll see 2x. Here the current flow will be 4x, and so on. Now what these D1 and D2 and D3 are doing are, these transistors are just working as switches. You know that if the gate to source voltage of a NMOS transistor is more than the threshold, then that transistor is on. Otherwise, the transistor is off. So if your gate voltage over here is, let's say, 3.3 volt, for example, let's say these are 3.3 volt transistor. So you're applying 3.3 volt over here at the gate, which means that this gate to source voltage, assuming that the voltage over here is, let's say, much lower than 2.6 volt, then you will have a VGS of this transistor that is more than the threshold voltage of the transistor itself. That means this transistor will be on if you are providing a high voltage over here. On the other hand, if you're providing a low voltage at D2, let's say you're providing a 0 voltage at the gate of D2. So the gate to source voltage of D2 will definitely be lower than the threshold voltage of the transistor over here. So in that case, this transistor will be off. On the other hand, again, let's provide a 3.3 volt over here, or a 1, depending on the amount of voltage that you need to make this transistor on. So in this case, you have this transistor on, this transistor is off, that transistor is on. So you have a digital representation of 101. On the other hand, the amount of current that is flowing through these branches is that because this transistor is on, this switch is on. So you can imagine that, or you can assume that because the switch is on, this transistor becomes a short. So this current will flow through the W1 transistor. The second transistor, this one, is off, which means that you can consider it as an open. If the transistor is off, there is no current flow through it. That means it is open. So there is no 2x, even though 2x amount of current flow was possible, if this switch had been on, it will not be there because the switch itself is off. The 4x transistor, the switch is on again. So there will be a 4x amount of current flow through this branch. So what would be the total current flowing here? It will be 1x and this 4x. So there will be 5x amount of current flow through this in total. And again, 101 represents 5, right? If you are converting this digital data to analog information, or if you're just converting 101 to equivalent integer numbers, it's 5. So as you see that this current meter can be used in the digital to analog converter. Okay, so that's one application of it. Question? This is something we discussed in the previous class as well, right? So you have the ratio of the transistor. So how does current meter work? You have I1 current in here, and there is a particular amount of current, let's say I2 current over here, and you have a current meter circuit, right? So this is something we discussed in the last lecture, that this is called a current meter circuit because it can create a mirrored version of the original current just by and you can go through the derivation to understand why it is mirroring the input current. But you can also, instead of just directly mirroring the current, you can create any integer or fractional multiple of the input current as well. And that just depends on the ratio of the device transconductances between this MOSFET and that MOSFET. Okay, so if you are, and because device transconductance is nothing but mu times COX times W over L, if mu, COX, and L are same, all you need is a ratio of W or ratio of width. So if this transistor has the same width as the W0 transistor, then there will be a 1x current flow here. And if this transistor has a 4 times width as that of the W0 transistor, the 4x amount of current will flow through this branch. More questions? So you generally do not have a gigabyte size DAC, or you generally do not have a gigabyte size ADC. So the ADCs are usually 8-bit ADCs. So you do not have 1000-bit ADCs. They do not even exist in this world. The maximum that exists in this world is probably in the range of, let's say, 32-bit ADC. Okay? So you do not need more than 32-bit ADCs, because with 32 bits you can represent anything between 1x and 2 to the power 32 minus 1. So what is 2 to the power 32? That is a very, very large number. Right? So you have a huge dynamic range between something that is 1 time and that's the minimum that you can represent with 32-bit ADC or that, and the maximum that you can represent is 2 to the power 32 minus. So there is, and that itself is more than 1 billion in that. So 2 to the power 20 is a million, 2 to the power 30 is a billion. So you can represent something within 1 and 1 billion if you have a 32-bit ADC. So there is no existence of a billion-bit ADC that will be a billion 2 to the power billion. So just imagine how big that number will be. Yeah, more questions. Yeah. You can. So it's just that your width has to be 4 times. And you can do it in whatever way you want. You can have the width as 4 times, or you can put 4 transistors in parallel. Okay. So some of the other applications of current meters is that you can use the current meter as an active load circuit. Again, something that we discussed before, that what is an active load, or what is a current source load, is that, for example, here you have a common source amplifier, right? You are having your input applied at the gate, your source is common, and your output is at the drain. What is the load for this circuit? The load for this circuit is the resistance that you see looking into the drain of this M2 transistor. And as you see, that M2 is a current source load. It is not a diode connected load. If it had been diode connected, the gate and drain would have been connected. Something like what you have on this side. So this is the current source load looking into the drain of the M2 transistor. So you'll see the RO looking into the drain of the transistor, you'll see the RO, the output resistance of the transistor itself. But how do you make sure that this transistor is in saturation, or is this transistor is biased correctly? This is one way to make sure that. So you have a current meter on this side, and you're using the same gate voltage of the current meter on this side as well. Now you remember, you know that if you have a diode connected transistor, it's always in saturation, because gate to source voltage is equal to drain to source voltage. So gate to source voltage for an NMOS, I'm talking about an NMOS, the gate to source voltage is definitely more than the drain to source, or the drain to source voltage is definitely more than. So let's call it this way, VGS minus VT. So this will always be true for a diode connected transistor, because for a diode connected transistor, VDS is equal to VGS. And that's what you have over here. And since you're connecting the same gate to the gate of the M2 transistor, the transistor M2 will also be in saturation. Assuming that, of course, this point, the drain voltage of the M2 transistor is not too different from the drain voltage of the left-hand side transistor. Someone asked about current amplifiers in one of the previous lectures. I think, Alessandro, you asked that how do you create a current amplifier? So current meters, if you have a ratio which is more than 1, it can work as a current amplifier. So MOSFETs do not generally work as a current amplifier in the strict sense that you cannot have the common source, common gate, or common drain stage work as a current amplifier. Because if you are providing the input at the gate, there is no current flowing into the gate, so you have no input current. If you are providing your input at the source, the same current flows into the drain and the source. So again, you do not have any amplification for common gate, common source, or common drain configuration. But using the current mirror, you can have current amplification. If you have 1x current at your input, you can create a 4x current at your output just by having a ratio of 4:1. So current mirrors do work as a current amplifier. All right, and you can also make them work as a fractional amplifier as well. So again, I think Michael, you asked this question that how you can, or whether you can put transistors in parallel with each other. And of course you can. So for example, on the left side, you are putting 2 transistors in parallel. That is equivalent of saying you are having 2 times the width of one individual transistor. On the right hand side, you are putting 3 of them in parallel. That means that you are putting, you are having 3 times the width of one individual transistor. So the ratio of currents you'll have in this case is 3/2 times the input current. Because at the output side, you have 3 of them, at the input side, you have 2 of them, and all the transistors have the same W, same width. If that is the case, then the I out will be 3/2 times I in. All right, so that's all about current meters that we wanted to discuss. But something else we wanted to discuss today is called a differential pair. And this will be very important in understanding how the internal circuitry of an op-amp works. And what you have here is, if you look closely, that you have a V1 input provided to a common source transistor over here, and you have another input V2 provided to the right-hand side common source transistor. So you have 2 common source amplifiers connected together at the source side, and then you have something called a tail current. Okay. You have something called a tail current source over here, which is used to bias these transistors. We'll come into more details of this tail current source. But right now, you can probably imagine this as a combination of 2 common source transistors or 2 common source amplifiers. And why is it called a differential pair? Because as you are connecting the 2 common source transistors in this way, it actually amplifies the voltage difference of V1 and V2. So it amplifies V1 minus V2. And again, why is that? Because as you see that you all of you know about superposition theorem, and there was a question on superposition theorem in your exam number 1, right? So if we apply superposition theorem here, how we can analyze this is that you have only this V1 voltage source first, and the V2 voltage source does not exist. Let's just assume it for a second. So there would be a current flow through the M1 device, okay, as you are applying a particular amount of VGS, or you are applying this gate voltage of V1. So this, let's say this M1 transistor is on, and there is a current flow through this M1 transistor. And remember that here we are talking about AC voltage. We'll assume that the DC is already established and all transistors are already in saturation. So there is a AC current flowing through this transistor from the drain to the source. Now that AC current sees 2 paths over here. One path can flow through this current source, and the other path will go here, right? But because remember that ideal current sources have infinite impedance. So looking down at this point, this current will see infinite impedance. So it will not take the path through this tail current source. So this is the DC current source, and the AC current flowing through the transistor will not take this path. Rather, all the current will flow back into this. Okay. On the other hand, if you consider the V2 the voltage source, so let's say you are applying superposition theorem, the second part of the superposition theorem, and there you assume that only the V2 source exists and V1 does not exist. In other words, V1 is, let's say, grounded in terms of AC. In that case, there would be a current flow in this branch. Now you see that this current and the previous current are in opposite directions of each other. And this is the reason why I said that you are trying to amplify the difference of the inputs, because one input creates a current in this direction, the other input creates a current in the opposite direction. So when you have both the inputs applied at the same time, the currents, because the currents are in the opposite direction, some of those currents will be nullified, right? So it's if you have let's say 100 millivolt input provided over here, and another 100 millivolt input provided as V2. And remember that these are all AC voltages. So you have a AC 100 millivolt as your V1. You have another AC 100 millivolt as your V2. the resultant AC current in the circuit will be 0. Because this 100 millivolt V1 will create a current in this direction. This 100 millivolt V2 will create another current in that direction. And these two currents will cancel each other by exactly the same amount. It will cancel them perfectly, right? So your output current will be 0 in that case. So how do you make sure that it can work as an amplifier? Provide the inputs as a differential version of each other. And we discussed about this, that differential input does not only mean that you're taking a difference of the input. It means that if one input has a 0-degree phase, the other input will have a 180-degree phase. Okay, so this will have a 180-degree phase at the input itself. If you're providing both inputs at 0-degree phase at the same phase, then they will cancel each other in the differential pair. Only if you have one input at 0-degree phase and the other input has 180-degree phase, the currents will perfectly add up. So if this has 0-degree phase, the current flows in this direction. If that one has 180-degree phase, this current will also flow in this direction, in the same direction. So those currents will add up because of KCL. Okay. So for a differential pair, anytime you want to make it operate as a differential pair, you have to apply the input as a 180-degree phase shifted version of each other. Okay. You can also apply only one input and not the other input. That's also possible. And in that case, the only disadvantage is that your gain will, we'll come to that. But here, for example, before going there, let's discuss one more thing. That, okay, you have a 0-degree phase as one of your inputs. So you are creating some amount of current through this branch. So let me clear this up. Okay, so you are creating some amount of input current because of this 0-degree phase input. On the other side, you have a 180-degree phase input. So that is also creating the current in the same direction. So if this current is I1, the current that is created by the N2 transistor will also be exactly equal to I1. So the total amount of current that will eventually flow is equal to 2 times I1, right? Because I1 and I1, two currents will get added up. One current is flowing because of the M1 transistor and the application of the 0-degree phase input at the M1 transistor. The other current is flowing because you are applying a 180-degree phase input to the N2 transistor. So total, you have 2 times I1 amount of current. Okay. 2 times I1 amount of AC current. Now let's say you are applying a load resistance over here. The voltage that gets developed across that load resistance, if you're taking that as your output, then that output will be 2 times I times R. Okay. So your total amount of voltage at the output has this factor of 2. On the other hand, if you had only one input applied and the other input is an AC ground, then you have a I1 amount of current flowing through the differential branch, and that will be multiplied with the resistance. And in that case, you'll be getting a voltage of I times R. So by applying a differential input voltage, you get 2 times I times R. That's the amount of output voltage that you get. If you are applying a 0-degree phase in one of the inputs and 180-degree phase in the other input. If you are applying a 0-degree phase in the one input, and if you're keeping the other input as an AC ground, you still bias it with a DC voltage, but you don't apply any AC voltage to it. Then the output is equal to I times R. So the output can also get doubled as you are applying both the inputs in a differential way. All right. So with this introduction, we'll go into this set of slides that I have for differential amplifiers, and we can discuss the rest of the things from the slides. Okay. So what we'll be discussing first is single-ended and differential operation. We'll discuss about basic differential pair. We'll also look at the common mode response and differential mode response of these kind of amplifiers. Now, first of all, single-ended operation. This is something that you have already know that you're applying a single-ended voltage. That means you're applying a voltage between a particular terminal and the ground terminal. right? So if you have that kind of a voltage, it's called a single-ended voltage. On the other hand, we have already defined differential voltages, and differential voltages are in 180-degree phase shifted versions of each other. Let's say you have one voltage applied at terminal X and the other voltage is applied at terminal Y. These are 180-degree phase shifted versions of each other. Right? So that's the definition of a differential input. It's not just that it's a difference of the input, it's also the fact how those inputs are configured. They have to be 180-degree phase shifted versions of each other if you want to call them as differential signals. Of course, there can be a common mode level. That's basically the bias DC level of the inputs. All right. So now, what is the advantage of this differential operation? The main advantage of the differential operation is that it gives you higher amount of immunity to environmental noise. So what is meant by higher amount of immunity to environmental noise? Let's just assume that you have a single-ended amplifier. You have a single-ended amplifier and you're taking the output of the amplifier using this line. The L1 is the signal line. And you expect a sine wave on this particular line. On the other hand, let's just assume that there is a clock line going through, or a clock signal, or a clock connector, which is very close to this signal line. So the signal line is a wire. There is another wire which is very close to it, and it carries the clock, which goes from 0 to 1 and then comes back to 0 again, and just keeps on switching over time. Because there is a parasitic capacitive coupling between the clock line and signal line, remember that any two terminals, any two physical terminals will have a capacitance between them. And that capacitance is parasitic. It does not exist as a physical capacitance, but it exists as a parasitic component. Now, because of this parasitic capacitive coupling, what you'll see on the signal line are these ups and downs as the clock signal goes up and down. So this is called interference. So your signal, your clock line will interfere with your signal line. So that's what will happen for a single-ended signaling. But if you have differential signaling, which means that you are having two lines. So let's say L2 and L3, these are your signal lines. And you have configured them in a way that they carry differential signals. So if one of the sine waves has 0-degree phase, the other sine wave will have 180-degree phase. And if right now, if your and your final output is a difference of this sine wave minus that sine, right? Because your input is a differential input, your output has to be a differential output. So the whole purpose of taking a differential signal is that eventually you'll just consider the difference of those signals. So if that is the case, and if you have a clock line going in between the L3 and L2 lines, so the clock will interfere with both of the sine waves in a similar way. As the clock goes up, you'll see upward going spike in this sine wave as well as that sine wave. As the clock comes down, you'll see a downward going pulse or a downward going spike in this sine wave as well as that sine. So the clock is interfering with both the lines in a similar manner, right? And similarly with noise, if there is noise in the system, noise will affect both the terminals in a very similar manner. So as you're taking difference of the signals, your sine wave will look very clean. So the sine wave will be 2 times more than or in amplitude, it will be 2 times more than the individual amplitudes of these sine waves, but it will be clean in terms of the interference from the clock as well. Because the way the clock affected the sine wave was that there was a upward going spike for both of these cases and a downward going spike for both of these signals at the same time. So that's the biggest advantage of having differential operation. Same thing happens with noise. So let's say you have your supply voltage is noisy. So all of you are doing your labs and you know that even though we say a DC signal is a fixed signal, a fixed 3.3 volt or a 5 volt or a 1 volt, it's not exactly fixed. So there is always some amount of noise in the supply. There is always some amount of noise in the biases and so on. But again, if the noise is on the supply, that noise will affect this output and that output in the exact same manner. So as you are taking the difference of those outputs, it will be a clean signal. So instead of taking a single-ended output, which will be noisy, if you take the differential output, there will be almost no noise at all. So that's one advantage of having differential operation, that your noise reduces, your effect of interference reduces, but what is the trade-off? Because there is no free lunch. So you have to, if you want something, you have to give something. So in this case, you are giving up on the area and the power consumption. So you have double the amount of hardware. Instead of one amplifier, you have two amplifiers together. So you have double the amount of area, you're consuming double the amount of power at least, and with that, you are getting the advantage that your noise and interference are becoming lower and lower. The effect of noise and interference are becoming lower and lower. Question? Mm-hmm. Right. Yes, because noise does not depend on your signal. Noise does not increase if you have a higher signal. Noise does not reduce if you have a higher signal. Noise is completely independent of your signal. So even if your signal is higher, it will still operate the same way. If those noises are correlated, yes. So why I said that this noise will go away, because both the circuits, so for example, this particular transistor and that particular transistor, both are connected to the same supply line. So whatever noise is present on the supply line comes at the output of both of these common source amplifiers, and because of that, when you take the reference, they go away. But at the gate, it depends on from where the gate signals are coming from. If they are coming from correlated sources, where you have where one source is dependent on the other source by some manner. So let's say you are trying to apply a DC voltage from the same source. So let's say you have a DC voltage with which you are trying to bias this transistor as well as that transistor. In that case, they are correlated, and the noise on the gate will go away if you are taking the differential. But if they are different sources, then this might not be the case. All right. So this differential operation is beneficial for any kind of sensitive signal. So if your signal line is sensitive, you would always like to have differential signal. Now, it may not only be in terms of the signal. So for example, in the previous case, you looked at analog signals, right, where there was only one clock line. So both the analog signal was single-ended, the clock line was single-ended. And when you went to a differential analog signaling, it helps. It can also help if your aggressor becomes, or the noisy line becomes a differential line, right? So the sensitive signal will be called the victim in the case of when you have these kind of interferences or a lot of signal that you don't want. And these noisy lines or the interferers are also called aggressors. Okay, so this is again a terminology that people generally use for wireline communication, victims and aggressors. Now, here the victim is basically the signal line L1 and the aggressors are L2 and L3. But now, interestingly, if you have your aggressors as differential, so let's say you have clock and clock bar going together in parallel with this L1 line, then they will affect the lines in the same way. So if clock goes high, clock bar goes low. And effectively, you do not have any spike on the signal line, even though both L3 and L2 are capacitively coupled with the L1 line. But of course, this is not very easy to do because the distance between L1 to L2, so let's say this is 1 micrometer. If this other distance is exactly 1 micrometer, then you'll see that, okay, there is no effect of the aggressors on the victim. But if this becomes 1.1 micrometer, then the parasitic capacitances will be different, the amount of interference from the two lines will be different, and eventually you'll see some amount of spikes. Also, the fact that how do you exactly create clock and clock bar? That is, you put an inverter in between. That you invert the signal so that when clock goes high, clock bar goes low. When clock goes low, clock bar goes high. So that inversion has some delay into it. And because of that delay, you'll see that the exact time instant when clock goes high will not be the exact time instant when clock bar goes low. And if there is a small difference in timing, then also you'll see that this method may not work perfectly. But theoretically, this will also work. Okay. What are the other advantages? Differential signaling increases the maximum achievable voltage swings. Because for single-ended signaling, let's say you have a 100 millivolt signal at your output. Let's say this is 100 millivolt. In case of differential signaling, you have a 100 millivolt at the first output and another 100 millivolt at the second output. So when you take the difference of the two signals, as they are 180 out of phase, the final output signal becomes 200 millivolt peak to peak. Right? Because when this is at the peak, this is at its bottom. When this is at the bottom, when it experiences the trough, then this is at the peak. So the final output signal will be 2 times as large as any of the individual signals. Okay, so that's what we are mentioning over here, that for the above differential circuit, the maximum output swing at X or Y at any of these points will be equal to how much? The maximum swing at this point. And why we are calling it that the maximum can be only be VDD minus VGS minus VTH. That's because what is VGS minus VTH? VGS minus VTH, if you remember this curve, that if you plot your VDS of the transistor across the x-axis and ID of the transistor on the y-axis, we know that the transistor is in saturation after this point, right? On the right-hand side of that point, your transistor is in saturation. And what is that point? That point is VDS equal to V over drive. When VDS is equal to V over drive, after that point, your transistor is in saturation. What is the value of V over drive? V over drive is VGS minus VTH. So at this point, the minimum voltage that you require for the transistor to be in saturation, the VDS, the minimum VDS that you require for the transistor to be in saturation is equal to V over drive. So at the output, let's say you have a signal that looks like this. Maybe let me see if I can erase some of this. Yeah. Okay. So at the final output, you have a AC or a sine wave signal that looks like this. So there is some common mode or there is some DC potential, and then there is an AC sine wave on top of it. What we just discussed, that the minimum voltage at point X needs to be equal to V over drive. And when do you have the minimum voltage at point X? When this sine wave reaches its minimum point. So even when the sine wave reaches the minimum point, it has to be at least equal to V over drive, at least equal to VGS minus VTH. So this point is VGS minus VTH. VGS minus V threshold or the overdrive should be equal to this minimum point if you're trying to go for the maximum amount of swing that you can have. And the maximum point, it cannot be more than VDD, right? So your supply voltage is VDD, so there cannot be any voltage in this particular circuit that will be higher than VDD. So this highest point on the sine wave should be equal to VDD. And the lowest point of the sine wave can be equal to V over drive. So what is the total amount of swing? What is the total maximum amount of swing possible? That is VDD minus V over drive. Right? So that is the maximum output swing at either the point X or point Y. That individually, that output swing can only be VDD minus V over drive. But if you take Vx minus Vy, that swing becomes 2 times VDD minus V over drive. So you can get a larger amount of output swing if you're doing the differential operation. Okay. So as an introduction to the differential pair, how does it look like? You already know the common source amplifier. So a common source amplifier looks like this, right? So you just have 2 common source amplifiers, put them side by side, apply Vin1 to one of the gates, apply Vin2 to the other gate, and make sure that Vin1 and Vin2 are differential in nature. Okay, that will give you the basic differential pair. that your output, if you're taking Vout1 minus Vout2, that would be 2 times, or that would be the gain of, so maybe let me write it down. So Vout1 is equal to gain, that is A times Gain1. Vout2 is again the same gain. Let's just assume that the gain of these two common sources are equal, that the transistor sizes are exactly equal, the resistances are equal, so the gain will also be equal. Right? What is the gain of this common source? GM times RD. If GMs are equal, the value of RD is equal, then the gain A will be equal. So Vout2 will be A times Gain2. So the final output, which is Vout1 minus Vout2, so let's just call it Vout, will be A times Gain1 minus A times Gain2. Now remember, Gain1 and Gain2 are 180-degree exact opposites of each other. So Gain1 minus Gain2 is equal to 2 times Gain1. So Vout will be 2 times A times Gain1. So that would be the final output in this. You can also represent it as A times Gain1 minus Gain2, because Gain1 minus Gain2 is equal to 2 times Gain1 because of the differential nature of it. So this is the basic differential pair. Now, yes, question. Yeah, so your output is right now here. It's 2 points. It's Vout1 is output, Vout2 is also output. You're considering the difference of those two outputs as your final output. So you always measure voltage between 2 points in your circuit, right? What are those 2 points? Usually it is Vout1 and ground, or Vout2 and ground. Now instead of putting the positive terminal of your oscilloscope to Vout1 and negative terminal to ground, you'll put your positive terminal to Vout1 and negative terminal to Vout2. And in that case, you'll see double of the swing that you see in either of those cases. Okay, so that's exactly what we are discussing in this slide. That okay, as you are taking these outputs, your V1 and V2 may look like this. Your Vout1 and Vout2 will be an amplified version of those two, like in a single-ended fashion. But when you take difference of those two, that is, you connect your positive terminal of the oscilloscope to Vout1, negative terminal to Vout2, you'll see double the swing of the individual Vout1 and Vout2. Now, what can happen is that if you are not biasing it properly, so in this case, again, as you know that biasing is a very important thing. So if your input voltage is too low, your output voltage will be too high. Again, remember, VTC curve looks like that. If your input voltage is too low, if your input and output both are almost equal to VDD over 2, then it's probably the perfect scenario. But if your input voltage is too low, let's say we are over here, but your input voltage is lower than the ideal what input cue point you should have had, then your output voltage could be too high. On the other hand, if your input voltage is too high, your output voltage could be too low. So if your input voltage is low, which is this case as compared to that one, so this is the correct one and this is the wrong one. So you should not have an input voltage that is too low. What would happen in that case is that your output DC point will be at a much higher voltage as compared to this. So this is correct, and again this is wrong. Why is that? Because your output DC voltage is too high, and because of that you will not get the full sinusoid. So this full sinusoid should have looked like that, but you'll not get the full sinusoid because you are getting clipped by the VDD voltage. And as you know that there cannot be any voltage higher than VDD in your circuit, this is, instead of a sinusoid, you'll get a clipped sinusoid at your output. So you should not have your input DC point too low or too high, that will cause clipping. So let's stop here for today. In the next lecture, in Wednesday's lecture, we'll discuss more details about the differential pair, and we'll see what is the need for this tail current source, how to analyze the differential pair, and what are different versions of the differential pair that you have.